Hello everybody, this video is going to be a reminder about the reaction quotient and how it's different than the K value, and also how we can use ice tables to do some of the math in this chapter. So first, when we have a container and we've dumped in our reactants and products and we're not at equilibrium, or maybe we don't know whether or not we're at equilibrium, we can mathematically calculate whether or not the reaction will go in the forward direction or the reverse direction. What we're going to do is compare the current concentrations of our system to what they should be when they're at equilibrium by looking at the equilibrium constant. When we take the ratios of our products to reactants, just like when we're calculating K, but when we do this with the quantities that are actually in our beaker at that moment, we don't call it K. We don't call it the equilibrium constant. We call it the reaction quotient. We use a capital Q. This is what we use when we aren't sure whether or not we're at equilibrium yet. The nice thing is, if we want to mathematically set up our reaction quotient, we do it exactly the same way as if we were calculating K. It is still products on top raised to their coefficients divided by the reactants on the bottom raised to their coefficients. Or you could do pressures if you don't have concentrations, right? You could do pressures. The thing is, the values that you're going to plug in here may not necessarily be the same as what they should be at equilibrium. Your Q will probably not match your K value. It's probably not very, statistically probable that if you randomly dump chemicals in your beaker, you're going to get exactly the right ratio to instantly be at equilibrium, right? You're probably just dumping in a bunch of chemicals, either resulting in too many products being there, too many reactants being there, right? We're going to have to calculate where exactly we are in this situation. If your Q value happens to equal K, then you are at equilibrium. If Q is larger than K, that means you have too many products, right? Your numerator is too big. And so if your numerator is too big, in order to get to your K value, you're going to have to go to the left trying to use up some of those products, trying to make more reactants so that you end up at your K value. Now, if your Q value is too small, if Q is less than K, that means your numerator is too small. You don't have enough products. Your denominator is too big. You have too many reactants. So your reaction is going to shift to the right, trying to use up some of those reactants, trying to make more products until you can reach your equilibrium position. Sometimes people find it helpful to look at this on a graph style image instead of just thinking about numerator versus denominator. So hopefully this helps some of you. If Q is bigger than K, that means we're up here. Okay? That means we're up in this area. We have too much product present. The reverse reaction is going to take place to try to bring us down to our equilibrium position. It's trying to go backwards until it gets here. If Q is too small, that means we're down here. So the forward direction is going to proceed to try to get us to our equilibrium position here. We're going to be making more products trying to get up to here. Now, if you're really, really lucky, somehow you magically manage to dump in exactly the right amount of stuff and you're already at equilibrium. You plug in all your numbers and you go, oh my gosh, Q is equal to K. So I'm at equilibrium. Sometimes people get a bit stumped if they have a scenario where all they have is reactants or all they have is products. They try to plug things in to their equation and they don't stop to think about the logic, kind of the common sense scenario. If you have nothing but reactants, how could you go backwards? You have to go forward. If you have no product, you have to go forward. You have to make some to get to equilibrium. So if you plug in your numbers and Q ends up being 0, then you have to go forward. You don't have any product yet. You got to make some. If all you have is product, you plug in your numbers to your calculator and your calculator freaks out at you because you're trying to divide by 0. And it doesn't like that, does it? And then people freak out because they're not stopping to think about the common sense here. If you're way up here and you have no reactants present, the only possibility is for your reaction to go backwards. It has to start making some of those reactants. It's going to go backwards. So don't freak out when your calculator goes crazy because you're trying to divide by 0. Stop with the math for a minute and just use some common sense. If I don't have any reactants, I'm going to have to make some. So if we know a value for K, and we have some information about the system, how much is there, we can figure out what the concentrations would be at equilibrium. What you would do is you would use what's called an ice table. We use ice tables a lot. So let's say we do this problem here. Assume you start with 8 moles of water, 6 moles of carbon monoxide in a 1 liter container. What is the concentration of each thing once we finally reach equilibrium? You always want to make sure you start by writing out your law of mass action. The nice thing here is that we do know the K value. Sometimes, right, you're trying to solve for K when you know the equilibrium concentrations. But this time we were given the K value. We're trying to solve for these things in here. So what we would do is we would use an ICE table. It stands for initial, the change that's going to occur, and what will it be at equilibrium. I highly, highly suggest that you somehow in your notes make a big, obvious note to yourself to check your volumes. They will often be giving you moles in a 1 liter container. But if it was a 2 liter container or a 1.5 liter container, you may make a mistake and plug moles into your chart and not concentrations. Remember, concentrations is moles per liter. So if you don't have a 1 liter container, you have to mathematically make sure you're converting into concentrations. Please be careful about your volumes. So the problem told us that we had 8 moles in a 1 liter container, so we had 8 molar of water gas, 6 of carbon monoxide, and we didn't start with any of our products, did we? So just put in a 0. Based on the stoichiometry of this equation here, these are just 1s for my coefficients, right? So when our reaction proceeds to the right, we lose X of H2O, we lose X of carbon monoxide, we make X of H2, and we make X of CO2. If you didn't have 1s for your coefficients, you'd have to include them here. You might say, oh, 2x or 4x or whatever. At equilibrium, we would have started with 8 and we've lost x. We started with 6, we've lost x. X and x. 0 plus x. One quick thing, if you aren't obviously starting with no products here, or you don't start with no reactants, therefore you know you're going backwards, you do need to calculate K versus Q. You need to determine which direction the reaction's going to go, because you don't know which ones in this row would be negative and which would be positive. If we were proceeding to the left, then these would have been positive and these would have been negative. So always remember to calculate Q versus K if it isn't obvious what direction you're going. So now we know our equilibrium values, but they have X in there, right? That's not helpful. So what I'm going to do is I'm going to plug them into my law of mass action. I'm going to solve for X. People get this far, they get X, and they are so relieved to have finished all their horrible algebra. They're like, oh my gosh, I finally did my quadratic equation or whatever horrible algebra you had to do, and you find X. And they forget to finish the problem. The answer here is not 4. Okay, that's the value of X. But that's not the equilibrium concentrations for each of those substances. What you have to do is plug X into your equilibrium row. 8 minus 4 gives you your ending concentration. 6 minus 4 gives you your ending concentration. X and X is just 4 and 4. So these can get tricky. You can have to do some awful quadratic equations, right? Yuck. You should remember what the quadratic equation is from math class. If not, look it up and add it to your notes. The nice thing is we don't often have to do these. A lot of times we will have kind of some algebra tricks we can use, like what's called perfect squares, where you can take the square root of both sides and solve in a lot easier way. Or you can do the 5% rule. Do you remember that, where we were able to simplify? You can go back to your honors chem videos and look through that if you can't remember how to do the 5% rule. But basically, if X is really small, we can kind of ignore it for some of our boxes on our ICE table, which simplifies our algebra. And then, you might get some awful substitutions, rearrangements, etc. But the concept is always the same. You're always plugging into an ICE table and trying to solve your values. You do need to practice. I'm not going to sit here in this video and go through a bunch of practice problems because there's just too big of a variety. Showing you 1 or 2 isn't actually going to do much good to help, because you have to start seeing huge variety of samples here. So doing your practice problems for these chapters is incredibly important, because you're going to have to practice a variety of ICE tables. You're going to have to practice doing 5% rule and perfect squares and quadratic equation. You're going to have to practice connecting things back to the kinetics chapter and connecting things back to the, thermodynamics chapter. You're going to have to sometimes manipulate your K values, kind of like a Hess law problem. There's going to be so many different ways these problems get applied that it's just going to be more efficient to be doing them in your practice problems. Okay, so make sure you're paying really good attention to those this chapter. It's really important. All right, everybody, that is it. I hope that was helpful. Bye.